Aluminum foils have been widely used in food and pharmaceutical packaging in order to maintain the freshness of these substances for a long span. Over the years, aluminum foil has been considered as an impressive kitchen utility used by people for preserving mainly food items. How has modern technology helped in the effective making of these aluminum foils? Does aluminum foil serve as a perfect lubricant for preserving food items? What are its impressive advantages that caught the eye of the masses? In 1910, Robert Victor Nair was the one who took out a patent for the continuous rolling process and opened the first aluminum rolling plant in Kreuzlingen, Switzerland. Later on, Toblerone's impressive aluminum foil packaging implemented by burn-based Tobler caught the attention of the masses. Aluminum foil has successfully conquered the packaging market for butter and cheese over the initial years. Aluminum foil has been proposed as a packaging material for butter at the World's Dairy Congress in Berlin. In 1948, Europe, the first aluminum foil food containers were used for bakery products appearing on the market, followed by a variety of other food items. Not only was it concerned with the packaging of food items, but was also used for technical applications, such as industrial products including fats, waxes, and adhesive compounds. Aluminum foil offers multiple benefits with its lightweight flexibility, temperature, retention, and can be easily recycled according to our needs. Foil sealed for freshness, aluminum has the excellent preservation properties applicable for almost all packaging applications used in every conceivable market, from food and drink to pharmaceuticals. The making process of aluminum foil. The manufacturing process begins by extracting pure aluminum from bauxite that involves mainly two processes. At first, the ore is refined in order to eliminate impurities such as iron oxide, water, silica, etc. The aluminum oxide is smelted in order to produce aluminum. And finally, the aluminum is rolled to make the resulting aluminum foil. Bayer process that includes digestion, clarification, precipitation, and calcination is used in the refining process of bauxite. During its digestive stage, the bauxite is grounded and mixed with sodium hydroxide before being pumped to the large pressurized tanks. In these digesters, the combination of sodium hydroxide, heat, and pressure breaks the ore into a saturated solution of sodium, aluminate, and insoluble contaminants which settle to the bottom. The next phase of the process, clarification, entails sending the solution and the contaminants through a set of tanks and presses. During this stage, cloth filters trap the contaminants, which are then disposed of. After being filtered once again, the remaining solution is transported into a cooling tower. In precipitation, the aluminum oxide solution moves into a large silo in an adaptation of the DeVille method. The fluid is seeded with crystals of hydrated aluminum to promote the formation of aluminum particles. Calcination entails exposing the aluminum hydrate to high temperatures. This extreme heat dehydrates the material, leaving a residue of fine white powder aluminum oxide. Smelting separates the aluminum oxygen compound produced by the Bayer process, and the next step is extracting pure metallic aluminum from bauxite. The procedure currently used derived from the electrolytic method invented by Charles Hall and Paul-Louis Toussaint-Héroux. First, the alumina is dissolved in a smelting cell, a deep steel mold lined with carbon, and filled with a heated liquid conductor that consists mainly of the aluminum compound cryolite. An electric current is run through the cryolite, causing a crust to form over the top of the alumina melt. When additional alumina is periodically stirred into the mixture, this crust is broken and stirred in as well. As the alumina dissolves, it electrolytically decomposes to produce a layer of pure molten aluminum on the bottom of the smelting cell. The oxygen merges with the carbon, which is used to line the cell, and it escapes in the form of carbon dioxide. In molten form, the purified aluminum is drawn from the smelting cells, transferred into crucibles, and emptied into furnaces. The liquid is then poured into the direct chill casting devices, where it cools into large slabs called ingots or re-roll stock. An alternative method to melting and casting the aluminum is called continuous casting. This process involves a production line consisting of a melting furnace, a transfer system, and a casting unit. After the foil stock is made, it is reduced in thickness to make the foil. This is accomplished in a rolling mill, where the material is passed several times through metal rolls called work rolls. As the sheets of aluminum pass through the rolls, they are squeezed thinner and extruded through the gap between the rolls. The work rolls are paired with heavier rolls called backup rolls, which apply pressure to maintain the stability of the work rolls. This helps to hold the product dimensions within tolerance. The work and backup rolls rotate in opposite directions. Lubricants are added to facilitate the rolling process. During this rolling process, the aluminum occasionally must be annealed to maintain its workability. As the foil sheets come through the rollers, they are trimmed and slitted with circular or razor-like knives, which is installed on the roll mill. Trimming refers to the edges of the foil, while slitting involves cutting the foil into several sheets. These steps are used to produce narrow, coiled widths in order to trim the edges of coated or laminated stock and to produce rectangular pieces. Finally, when the foil is in its final state, it is packaged accordingly and shipped to the customer. Does any other packaging utility have the incredible feature that will be able to compensate for our needs replacing the aluminum foil? Let us know in the comment section. Don't forget to subscribe to our channel for more content just like this, and be sure to hit that like button too.